In this session, let us solve a question from JEST 2024. The question is from group theory. Here we have a group of order 4 and its multiplication table is given. The group elements are identity A, B and C. We have to identify the type of the group. Is it cyclic or non-cyclic, and is it abelian or non-abelian? So let us go to the definition of cyclic group. A group is cyclic if there exists an element small g belongs to capital G such that the group G can be written as G raised to n. N belongs to Z. Z is the set of integers. Here what we mean by G raised to n is not G into G into G. It is not the multiplication. G raised to n, or let's say for example G cube, this is not equal to G into G into G, but this is actually equal to G operation G operation G. Now this operation, it can be multiplication, it can be rotation, or it can be any other operation as well. So in words, we can say that a group is cyclic if there exists an element. This element is also called a generator. So if there exists an element that can produce all the other elements by repeated application of group operation. An example would be G is equal to 1 I minus 1 minus I. Whenever we define a group, we have to specify the group operation as well. So this group under multiplication G is a group. Now we say that this group is cyclic. Why? Because we can obtain all the other elements by repeated application of group operation on the element I. So I raised to 1, this is equal to I square, this is equal to I. Operation here is multiplication. So I into I, this is equal to minus 1. I cube is equal to minus I. I raised to 4 is equal to 1. So we are obtaining all the other elements by the repeated application of group operation on the element I. Therefore I is called a generator. There can be more than one generator in a group. Now there is a rule: if a group is cyclic, of order n, then at least one element, if a group G is cyclic of order n, then at least one element of G has order n. Now it is given that the group here, it has order of 4. Now even if it is not given, we can find this out, because order of group is nothing but the number of elements. Number of elements in the group is 4, so the group order is 4. Order of group is equal to number of elements in the group. This is equal to 4. Now if group G is cyclic, then we need at least one element of G to be of the order of 4. Now what is the order of an element? Order of element in a group. Let's say we have to find the order of element A. Then the order of element A is the smallest positive integer, let's say n, such that A raised to n, A is the element, element raised to n is equal to identity. So n is the order of element A. So in our problem we have the order of group is equal to 4. Now for the group to be cyclic, at least one element of the group, it should be of the order 4. Let's see. So if A is of order 4, then we need A operation, A operation, A operation, A. This is equal to identity. And A operation, A operation, A. This should never be identity. A operation, A. This should never be identity. So let's see. A operating on A. This gives us identity. So A is not of order 4. In fact, A operation A is equal to identity. This implies A is of order 2. Similarly, if you see B operating on B, this gives us E. C operating on C gives us E. So C operation C, this is equal to E. C is of order 2. Because C square is coming out to be identity. Therefore, we are saying this 2, it is the order. And similarly, you can see B operation B, this is also identity. So B is also of order 2. B is of order 2. Now identity also can never be order of 4. Therefore, we say that this group is not cyclic. Because for the group to be cyclic, at least one element has to be of the order of the group, which is 4 in this case, but none of the elements have the order equal to 4. Now let us check if the group is abelian or not. So abelian, a group is abelian if H operation G is equal to G operation H. For all H and G belongs to capital G, if H operation G is equal to G operation H, then we say that G is abelian. Let's see. Here you can see A operating on B gives us C. B operating on A gives us C. So A operation B is equal to B operation A. Both are equal to C. Similarly, you can see this B operation C is equal to A is equal to C operation B. For any other elements in this group, this is followed. H operation G is equal to G operation H for all H and G belongs to capital G. Therefore, the group is abelian. Option A is the correct answer here. One way to easily identify the group is abelian is that in the multiplication table you can check for symmetry across the diagonal. So this is our diagonal. This is the diagonal we have. So we can check the symmetry. At the first row, in the second column you have A, and in the second row, first column also you have A. So there is symmetry. In the first row, third column you have B. In the third row, first column you have B. So there is symmetry. You can see here is C, here is another C, here is A, here is another A, here is B, here is another B. There is symmetry across the diagonal. So that's the property of abelian group. In the multiplication table, there is symmetry across the diagonal for an abelian group. That's it for this session. Thank you.